Okay, so that's what I said here. Okay, so these are the answers, and these are what I said. Okay, so high energy conversion efficiency is very, very important. Okay. Yeah, again. Okay, so if no problem, then keep going. Okay. Yeah. So this is this the last? No. Uh, the other subtopic. Okay. So so in this subtopic, just want to introduce you two main structures of our electronics interface. So no matter what we want to do with the power electronics interface, for example, DC, AC, and so on. Okay, and we have the very similar diagrams. We still need to rely on two main types of power electronics interface. Okay? So the first one is voltage link structure. So this is the typical examples of voltage link structure. So it is very quite easy to differentiate. Okay, so from this picture we can see that there is a capacitor. Okay. Oh, sorry, I need to change to pen. Okay, so we can see that there is a capacitor, right, connected in parallel between two sources. We can say that, right? So this is one of the source, and then two. But actually, I said that, right? One of the beauties for using the power electronics interface is that the power can be bidirectional. Okay, so anyhow here we have two sources, or one source, one load, and then there is a capacitor connected in parallel between them. Okay, so this structure has this some features. So it is very good at very large power range. So from a few tens of watts to several megawatts. Okay, so or even extending to even higher watts. Okay, for utility applications. Okay, and here CONV stands for converter. So converter 1 and then converter 2. So you will learn this converter, the operation, the principle of these converters in second half of this subject. And then the other structure is current link structure. So this is the current link structure, and here we can see that there is a inductor connected in series between two signals. Okay, two signals. So this is AC one, and then this one is also AC. Okay, so this structure is can be used at extremely high power levels. So this structure, when we use this structure, this should be utility related. Okay, utility related. So it is quite different from this one. So for example, previously, in some final year projects, we can also see students use this kind of structure to for motor drive. Okay, but they will not use this kind of structure. Okay, and then this one is the Forester. So you will learn this also from Dr. Yang in the second half of this semester. And actually in the simulation lab, you will also, is this? Yes, in the simulation lab, you will also use this kind of device for your circuit. Okay, that may probably before the lectures by Dr. Yang. Okay, it is because as mentioned at very beginning, we need to run the online simulation lab. Okay, so the period could be quite long. Okay, so most of you may do the lab first and then learn more in details from Dr. Yang later. Okay. Okay, so back to here. This is a current link structure. We can use this kind of connection So to differentiate between voltage link structure and current link structure. So here we have the inductor connected in series, okay, and this is again a thyristor converter. Okay, so let's do a comparison again. Sorry. Okay, so again, voltage link structure, there is a capacitor sandwiched or connected in parallel between two signals, okay, and then current structure, we can see that there is a inductor connected in series between two signals. Okay, so the other subtopic actually, of course, it is related to the previous one. So previous one, we just learned voltage link structure and current link structure, right? So here actually, from this diagram, we can find those two structures, right? So the first one is here, right? This is because there is a capacitor connected between two signals. So here is the input and there is the output, right? And then here we also have the inductor connected. So here is the load, and here is the load, and here is also kind of input. Okay, so in somewhere in between there is an inductor connected in series. Okay, so this is the current link structure and this is the voltage link structure. And when combine them together, so this is a typical topology for switch mode conversion. Okay, switch mode conversion. So here we can see there is a switch. We call it a bidirectional switch. Okay, and then this is the result. Okay, so actually we can get some ideas. Actually, this topology gives us a very fundamental knowledge or technique of power electronics interface. Okay, so here we have the DC input, and then here is the switch. So the switch can be up or down, controlled by the Q signal. Okay, so when QA is equal to 1, so it is up, otherwise it is down. Okay, so when the switch is up, so the current can flow through the switch and then to the inductor, right? When QA is 0, so the switch is down. So it means that here the current cannot flow through the switch to the inductor or to the load. Okay, so in that sense, we can imagine our resultant waveform. Okay, so when QA is equal to 1, we should have VA. Okay, so here actually QA is equal to 1, right? This is because when QA is equal to 1, the switch is up and then the current can flow through, so there is a VA potential difference, VA. Okay, and then when VA is equal to 0, so when QA is equal to 0, the switch is down, and so there's no VA. Okay, so here QA is equal to 0. Okay, and then repeat. Okay, so here is one cycle. Okay, so that is the main idea. Okay, how this kind of conversion, switch mode conversion works. Okay, okay, so actually I just mentioned this, right? So QA is equal to 1, QA is equal to 0. So actually here just spend. Okay, so when QA is equal to 1, VA, of course, from this topology, VA should be equal to V in, right? So when QA is, once again, when QA is equal to 1, it is up. So VA is equal to V in. Okay, when QA is 0, so the switch is down, right? Okay, so VA is equal to 0. So that's why we have these two waveforms. So one for QA, while the other one is for VA. Okay? And then the average. So in DC-DC converter, okay, So we need to calculate the average output always, okay, for all cases. Okay, so here, we have this equation, but actually from this equation we can find some interesting things that you need to remember actually. Okay, so one thing is here. This is V, right? But in small letter. This is also V, but in capital letter. Okay, so small letter means variables. It will change against time. Okay, variable. But for this one, it's a constant. Capital letter is a constant. It will not change. Okay, so let's see here. So VA is here, small VA, right? So it will change against time. So x-axis here is time. So we can see that this small VA can change against time, right? Sometimes V in, sometimes 0. Okay, but V in is a constant, is our input voltage. So with the capital V letter, okay, so it is a constant value. Okay, so from the letters, we can get some idea. Okay, so this is the variable, and with the capital letter, it is a constant. Okay, so similarly, there are two T, right? Capital T. So they are constant. They are constant. So this TS we call it switching interval. Switching interval. So here, one period we call it 1 TS, switching interval. Okay, it is because in this kind of topology, it keeps switching. It keeps switching. Okay, and the frequency from the application examples, we know that, right? So for induction heating, it can be up to 2 megahertz. Okay, so the switching is very fast. Okay. Okay, and this is TS, and the other one is T out. Okay, it's T out. So T out is the interval when the switch is up. Okay, okay, and so actually this ratio can determine our output. Agree? So just like a potential divider, right? Okay, so this is the ratio T up over TS. And with the input voltage, this is a constant, so it can determine our output, VA. And here, VAV, it is quite different from this one, right? So for this one, we have the other thing, the other one. There is a bar on top of the VA. So this one is average. All right, so this is the average value. So here, small VA is the variable, okay, but with this bar, it is the average. So in this subject, the average value will not change. But in practical, of course, it will change against time. Okay, but in this subject, things are steady. Okay, so this one here is the constant average. So here, the dashed line refers to the average value of the output voltage. Okay, and this one depends on the ratio of the T up and TS. Of course, also depends on the input voltage. Okay, and here the ratio can be termed as dA. Okay, so dA, this small d, is the duty ratio of the switching power pole A. So this kind of thing we call it switching power pole. Switching power pole. Why we term it A? It is because in practical there should be more than one switching power pole. Okay, so we need to name them A, B, C, etc. Okay, so each switching power pole should have its duty ratio and also the output voltage. Okay, so we need to the subscript for each of those parameters. Okay, and this DA duty ratio has the range. So the minimum is 0. So it means that when QA is equal to 0, okay. And then the maximum should be 1, okay. So if later, if you found that, okay, Jun Wei just left a message, right? Just left, I don't know. Yeah, I just saw that, okay. Why sometimes VA is equal to V in and QA is equal to 1. Let me think. VA is equal to V in. Oh, yeah. VA here should be equal to V in. It is because when QA is equal to 1, when QA is equal to 1, the switch is up. So when switch is up, so the circuit is like that, right? Okay, so we should have the VA, and the VA should be equal to V in, according to this topology. Okay, according to this topology. Is it okay? And when Q is equal to 0, so this is 1, and I may change the color. The blue. Okay, so when QA is equal to 0, so the circuit would look like this. Okay, blue light for the case when QA is equal to 0. So that's open, right? It is because the switch is down, connected to here. It's open here. Okay, so there should be no VA. VA should be equal to 0. Okay, so that's why we have this kind of waveforms. Okay, I hope that you know what I mean, Zhen Wei. Okay, and then okay, yeah, thanks. Okay, yeah, no problem. Stop me anytime. Feel free to ask questions. Okay, and DA, as I said, it has the range. So later, when you do the calculation, if you found that your value of DA is larger than 1 or even the minus value, there should be something wrong. Please check again. Okay. If no further question, keep going. Okay. So here actually, I will tell more details later. Okay. For the when that may be next week or after next week. Okay. Yeah. So actually, we use the same relationship shown in our previous slide. Okay. So now here we further expand the topology. So previously we don't have this output. Previously is open end. Now is with the resistor. Okay, we would name it V0. Okay, so actually here is the average, right? And I said that for the DC-DC converter, all the things are in steady state. Okay, so it means that the average value is a constant. Is a constant, and actually a DA is also the duty ratio is also a constant for a specific switching power pole. Okay? And then we will have further waveforms, and I will talk about that more in detail later. Okay? And here also searching more for information. And yeah, so here I just want to say that we know that we can. Here I actually need to deliver you the other message. Okay, so before that we can see that we use a switch, right? And this is a physical switch. And this one, we can't see there is a switch, but instead we have a combination of the transistor and diode. Why we want to have this kind of change? It is because we know that frequency, the switching frequency is very high, right? Can be up to megahertz. Okay, so the physical switch cannot do well for this kind of high frequency application. So instead, we can use this electronic switch. Okay, so the combination of the transistor and diode can act just like a electronic switch. Okay, and the detailed operation will be talked later in week 2 or 3. So anyhow, now we use this kind of thing to act like a switch. Okay, so the switching frequency can be very high, but it will have some criteria. Okay, the higher this, for example here, the higher the switching frequency, the higher frequency of the pulses, and the smaller the values needed for the low pass LC filter. So these are the practical stuff. Okay. However, if the switching frequency is higher, so it also means that the losses can also be higher. Okay, so in topic 2, you will know how to select the appropriate switch. So in terms of dial and also the transistor, there are many types of transistors and diodes. Okay, so topic 2 will give you some ideas. Okay, and this is the other example, example 1.2. Okay, so okay, so in this example, what is time now? It's 11. Okay, so we still have 20 minutes. 20 minutes. 20 minutes. Okay, yeah, we have enough time. Okay, so in this example, we also have a the topology of the converter. Okay, and then the input voltage is given, output voltage is given, and then ask you to calculate the duty ratio dA and the pulse width T out. Okay, this is T out or T. Okay, yeah, and then if the switching, this one is given. Yeah, if the switching frequency is 200 kilohertz. Okay, and then ask you to plot the waveforms of QA and VA. Okay, so please think about that, and then we may use 5 minutes to think about that, to draw your graph. Please try to do that together. It is because I want, before ending this lecture, I want to show you how I will mark your waveforms. This is just my approach, okay, to grade your waveforms, not represent Dr. Yang. Okay, Dr. Yang will have his own style. Yeah. So please try to think about the solution and draw the waveforms. Please try. Yeah. Actually, you can copy the previous waveforms in here. Actually, yeah, in 40, slide number 40. You can draw on your own. Okay. The waveforms are relatively simple, and then try to label, calculate, and then label the parameters. 5 minutes.